Thank you, Alicia, for giving most of my talk. I'd like to thank Dr. Russell also for inviting me, but just more than that, because truth of the matter is I'm quite an outlier, and I'm especially grateful for the invitation. Because although I was trained as a chemical engineer, I've spent my entire career as a theoretical ecologist. Now, most of you know that the dialogue between science and religion most of the time takes place between theologians on one side and physicists on the other side. And you know, they have slings and arrows and so forth and bullets flying back and forth. And here I am in ecologist in the middle of all this and say, hey, wait, maybe we have something to say. So that's what I've been spending pretty much the last 10 years of my career on. Ecology deals with life. Okay? Life in many manifold different forms, all clearly and strongly interrelated. Very important, because this is very, very different from physics. Life is not a thing, it's not an object, life is a process, or as Karl Popper put it, a network of processes. Now the world of physics, as Dr. Russell mentioned, is pretty much matter or objects moving according to law. And when you ask many physicists, including Nobel laureates like Murray Gell-Mann and Steven Weinberg and David Gross, say that, well, it's all from below, and if you look down there, there's nothing there but the laws of physics. Nothing but the laws of physics, the universal laws of physics. Now, what are those universals? Well, they're about 6 in number. There's gravity, electromagnetic, weak nuclear force, strong nuclear force. There's conservation of energy and entropy. You might be able to name 1 or 2 others, but they are, you know, just a few of them. The laws are universal, okay? They're descriptive, and if they're going to be universal, they've got to be described in terms of variables that are universal as well, which means that you have to neglect almost all the information. If I wanted to describe Dr. Russell in terms of gravitation, why I'd have to ignore who he is, what he is, his history, his physiognomy, etc., virtually all that's wonderful about him, and just talk about his weight, and which is fine. Virtually everything else is ignored. The problem here is that these universal laws cannot operate in a vacuum. They cannot operate alone. Any real problem, you've got to go back and unfold this and start specifying some of those things that you ignored in order to apply it to any real problem. And this specification is known as the boundary value problem. For example, if I want to know the trajectory of a cannonball, I need to invoke Newton's second law of gravitation, but I also need to specify where the cannon is, what the muzzle velocity is, and what the angle is, and probably several other things as well. And those specifications are called the boundary value problem. Now, the boundary value problem must be totally arbitrary, any way that you want to call it. It's up to the investigator, okay? There's a logical reason for that. If you could specify a boundary value problem for which the laws didn't apply, then they wouldn't be universal. Simple as that. They may, therefore, include the random. Whatever you may think of in terms of randomness, they may include the random. Now, another thing about the laws is 5 of the 6, at least, that I've talked about are all symmetrical. By that, it means that they look the same going forward in time as going back. If you had 2 billiard balls coming together and going apart, you wouldn't know which way was forward, which way was backward in time. The thing about the symmetry is that if you put randomness into something that's totally symmetrical, you get random out. Okay? You don't get order, you get random out. So we've got to look for something else. The boundary value problem can include the random, it can include the unique. Okay, the unique. And you say, well, how unique? And here I'm going to talk about our universe, the Hubble universe, not the multiverse, so forth. Well, think of it this way. There are about 10 10 to the 81st power quarks in the world, or maybe they're Higgs and maybe it's 10 to the 84th Higgs, but that's the sort of order of magnitude of all the particles in the known universe right now. How old is it? Well, it's about 10 to the 25th nanoseconds old. That's 13.7 billion years. Okay? So that if we multiply those two together, as Walter Elsasser, a physicist, said, we get an upper bound on the maximum number of simple events that could possibly have occurred in our universe. And that comes out to about 10 to 106. Let's say round it up to 10 to 110th. That's the size of our universe, the Hubble universe. And anything that occurs with a probability of less than 10 to the minus 106, unless there's something that will support it and keep it going, is simply not going to reoccur in several 100,000 repeats of our universe. Okay? So there is uniqueness. You might say, well, what sort of a system do you need to get to that, to 110,000? You don't need billions or millions or even thousands. About 80, almost the number of people we have in the room, of 80 distinguishable tokens will exceed 10 to the 110th. Essentially, such compound events are unique, won't reoccur unless they're supported somehow. Okay, I call this radical chance. And I concur with Dr. Russell that Monod was wrong. He was a false dichotomy. We're not dealing with just chance and necessity. We're dealing with a spectrum of contingency, going from radical chance to garden variety randomness, the normal type of distribution, which is very well described by the laws of statistics and probability, to conditional chance, like loaded dice, to propensities, what Karl Popper calls propensities, things that happen most of the time, but every once in a while they're a violation, all the way grading up into determinism, an entire spectrum. Okay, all this randomness going into symmetrical laws, where does order come from? Well, you've already got an idea of where it comes from now, thanks to our previous speaker. She talked about autocatalysis. Okay, Gregory Bateson said that if you put random input into a feedback system, you don't get random input out. And following our speaker's lead, we're going to talk about a subset of feedback called autocatalysis, wherein each element benefits the next element. A, you have process A, benefits process C, benefits B, process C, and so forth back to A. Now, there are a number of properties that this has when interacting with randomness or contingency that are rather non-mechanical. I will mention only two. Number one is selection. Okay, the idea is, suppose B is constituted of some characteristics. Suppose there's a slight change in a characteristic in B. If that characteristic either makes it a better catalyst of C or more sensitive to A, either or, then it will start receiving more reinforcement. Conversely, if the change makes it either a poorer catalyst of C or less sensitive to A, it will start getting less from A. It's against. There's a basic asymmetry in autocatalysis, symmetry breaking. Okay? Furthermore, I have A, B, and C. They don't just appear ex nihilo by and large. They have resources. Okay? And if one of the changes in B augments its ability to bring resources into the orbit, it will be rewarded. But that's true also of C and also of A. So that a second attribute of autocatalysis is what I call, or actually which was coined by Newton, centripetality. The idea that an autocatalytic configuration of processes draws resources, energy, and so forth into its own orbit. An extremely important attribute that all of life possesses, and nobody puts it on their list of necessary properties of life. Bertrand Russell called, he didn't call it centripetality, he called it chemical imperialism. And he said that it was the fundamental drive behind all of evolution. Now that's total heresy if you're an evolutionary theorist, okay? Because we all know that it's all competition and natural selection and so forth. But we now know that selection can occur not just from outside, but endogenously, from within the system, which again is another evolutionary heresy and so forth. So what I'm sort of describing is two tiers of law, if you will. At the very bottom, we have these universal foundational laws of physics. They are not violated. Okay, they're not violated at all, but they are insufficient to specify to the degree that we want to know. I would say that's epistemologically, but I think ontologically they're also insufficient to specify. What you have when you get autocatalytic configurations are what I would call proximate laws. The idea that they are historically contingent. Okay, the scenario that I just talked about in autocatalysis depends on contingencies. Okay, things that virtually cannot be predicted. But if a contingency really helps the autocatalysis, it becomes part of the overall system. Okay, it's taken into the system so that any structure that we see is historically contingent. Anything in this room or outside this room, I think you can trace to a contingency. It's not that the laws of nature are violated. It's just that there's been a contingency, or many, many contingencies usually, that brought them into being. We are all contingent beings. Examples of contingency, could be levo-dextro in biology, or RNA, DNA, the appearance. I don't happen to be a believer in naked DNA. Well, anyway, can't read that. So what's the theological take-home from all of this? Philip Hefner, who's a very, big individual in the theology and science dialogue, was once asked back in 2000, do you believe in miracles? And Dr. Hefner said, no, God just doesn't have enough wiggle room. Okay? Now, what we're saying here is that, yes, at the secondary level, at the thing that actually determines, there's a difference between being necessary and constraining and determining, okay? The universal laws are necessary and they do constrain, but they do not determine to the degree necessary to really constitute knowledge. So you have the foundational laws, and then you have these proximate laws that are essentially these structures that endure through time, that are stable through time. Most of them require some memory, not necessarily DNA and RNA. There are certain dynamical structures that are stable in and of themselves, but they're proximate. They're inherently contingent. There's lots of wiggle room in them historically, and there's room for God to act. I would say that they're totally consistent with Neota, which Dr. Russell talked about, and in saying so, I don't necessarily say that he has to believe in the process view of the world that I tend to favor more. I'm saying that his view, which comes more from contemporary physics and quantum theory, and my view, which is more from the macroscopic and the ecological, exhibit a sort of consilience in the sense that they overlap with regard to that particular conclusion. I would finally end by saying that what I think we really need is a new metaphysic, because if once we go away from the world of objects acting according to law and into the world of processes, what we discover is we need to revamp our metaphysics in a systematic way. I've tried to do that, and I can't explain it all now, but I have a book out from 2009 called A Third Window, Natural Life Beyond Newton and Darwin by Templeton University Press. And That's pretty much what I have.
Any questions? So questions for Bob? Okay, I've got one for you.
Sure.
When you say a process view of the world, do you mean Whitehead?
Whitehead, okay. No, okay, I should have, I had this on my notes and didn't read it, thank you. I tend to look at process more in the terms of thermodynamics. Thermodynamics, those of you who are familiar with it, there are so-called state variables, which are very Platonic-like, you know, they're essences almost. And then you have, connecting those state variables, you have processes, which is always path-dependent, always dissipative and so forth. And in the world of thermodynamics, they're given secondary status, okay? But there's Bernardus Telligin had this theorem that if you look at reality in terms of forces and fluxes between objects in a linear world, you can draw an equivalent one in terms of processes, the thermodynamic processes. Now, we don't live in a linear world, obviously, but at least we have the potential for a different perspective on reality. So no, you know, I think it bleeds over into the Whiteheadian notion of process, but being an engineer and feeling most secure with thermodynamic processes, that's what I'm talking about.